All right, I believe that we are recording. Yep, we are recording. So let's go ahead and get started with homework 3 practice problems. I did add a blank sheet of paper or a black PDF thing because we are absolutely positively going to need it. So let's go ahead and get started. So find the difference quotient f of x plus h minus f of x over h, where h is not equal to 0 for the function below, which is 5x squared plus 2, and simplify your answer as much as possible. So f of x plus h minus f of x over h, that will be 5 times, you know what, let's just go ahead and do it on another piece of paper. Let's just go ahead and do it. So f of x plus h minus f of x over h, right? And we said that f of x is equal to, go ahead and see what that was again. I should have written that down or something. F of x is 5x squared plus 2. So that will be for us 5 times x plus h squared plus 2 minus 5x squared plus 2 over h. So what I essentially did was, with the f of x plus h, I substituted in x plus h into this function. That's what that means. In the function f, put in x plus h instead of just x. I did that there. And then f of x, I just subtracted that. So we're going to be subtracting the entire thing. Okay, so x plus h squared, that is x plus h times x plus h. All right, we can FOIL that if you're familiar with that. And that would give us x squared plus 2xh plus h squared. Right, so we have 5 times x squared plus 2xh plus h squared plus 2 minus 5x squared plus 2. And that is all over h. Okay. So not quite an intermediate step, but kind of. But kind of. All right. Let's do a little simplification here now. So is equal to 5x squared plus 10xh plus 10h squared plus 2 minus 5x squared minus 2. And that's over h. So we have a negative 5x squared and a positive 5x squared. That equals 0. We have a plus 2 and we have a minus 2. That equals 0. So I'm left with 10x h plus, 10h squared over h. Now they did tell us to simplify this as much as possible. All right. Okay, so this becomes, we can get a 10h out of there. Yeah, we could get a 10h out of both of those, and I'm left with x plus h over h. Those two divide out, and I'm left with 10x plus 10h. And there we go. That is that. All right. So again, just to recap, I put x plus h in here. I FOIL this. X squared plus 2xh plus h squared. I FOIL this part here. I get this. So the first function, f of x plus h, is 5 times that plus 2. And then we subtract f of x, which is 5x squared plus 2. The 5x squareds cancel each other out. The 2's cancel each other out. Right? And then you're just left with this. Simplify that. So we have 10x plus 10h. 10x plus 10h. Yep, that is it. All right, so let's go to number 2. Same thing, but a little bit more. Same difference quotient, only we have a rational function. Got to keep it interesting, right? So 1 over x plus 9. Same thing. I'm going to rewrite the, too much. I'm going to rewrite the difference quotient just as a matter of course. All right, f of x, f of x plus h minus f of x over h. And f of x in our case is equal to 1 over x plus 9, if I remember correctly. I do. All right, so difference quotient for this will be 1 over x plus h plus 9 minus 1 over x plus 9 all over h. I know that looks fun. Right. So the first thing, we have to get a common denominator for the our numerator. So these two bottoms have to be the same for us to be able to do this operation. So we're going to do that, and we're going to do that in the most easiest, in the simplest way possible. It's relatively easy. It's not very bad. I'm going to multiply, let me erase this, equals. I'm going to multiply this one by x plus 9 over x plus 9. And I'm going to multiply this one by x plus h plus 9 over x plus h plus 9. Okay, so these two you can multiply in algebra or in math. The x plus 9 over x plus 9 is always going to equal 1. So I can always multiply anything by this, and it maintains equality. Like, it doesn't change the properties of anything. The same for this. All right, it looks a little harder than it is. So intermediate step, I have x plus 9 over x plus 9, x plus h plus 9 minus x plus h plus 9 over x plus 9, x plus h plus 9. And that's all over h. Again, as always, apologies for the messiness. Writing straight up like that while seated is kind of weird. Okay, so a property, I shouldn't have written it red, but a property should be green anyway. A property that we use when we're dealing with fractions or rational situations is a over c plus b over c is equal to a plus b over c. Or namely, if I have two fractions or two rational expressions and the denominators are the same, then if there's an operation between them, I get to just combine them. I get to put them together. So that's what I'm going to do here. But when you do that, we have to ensure that we distribute that negative. So we have x plus 9 minus x plus h plus 9 over x plus 9, x plus h plus 9 over, all over, h. Okay, so the x is negative, the h is negative, the 9 is negative. So this becomes x plus 9 minus x minus h minus 9 over x plus 9, x plus h plus 9. And that's all over h. We're getting close to the end. So, oh, hold on. Cancel. Say cancel. Okay, so x, negative x, get it out of here. 9, negative 9, gone. So I'm left with, change colors back. So I'm left with negative h over x plus 9, x plus h plus 9 over h. Okay, there's a shorter cut math that I could do here to go ahead and finish this off, but I don't want to confuse you. Hopefully you're not confused. Okay, so what we'll do is we're going to change this. This line right here means divided by. That line, the fraction bar means divided by. That's where it came from. So this is negative h over x, x plus 9, x plus h plus 9 divided by h. If you remember anything about fractions, dividing by a number in h is the same thing as h over 1. Dividing by a number is the same thing as multiplying by its reciprocal. So this is equal to negative h over x plus 9, x plus h plus 9 times 1 over h. Okay, we have it right where we want it. H and h, they cancel out and they become 1 and 1. So we are left with negative 1 over x plus 9 times x plus h plus 9. And that's our answer. Fun, right? Very, 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 very much fun, I think. Okay, this problem wasn't very bad. I showed some extra steps here so you could understand what I was doing. Okay, but main idea, common denominators on this step. I remember you need a number. Common denominators on this step. Combine it on this step. Simplify, make cancellations on this step. This is the result. Divide by h, and you're left with your answer. So, not bad, not bad. Let us continue. Number 3. Suppose the functions f and g are defined as follows. F of x is x over x minus 6, and g of x is 8 over x plus 7. Find f over g, then give its domain using an interval or union of intervals, and simplify your answers. So, f over g is x over x minus 6 over 8 over x plus 7. Now, of note, g is on the bottom, so any domain restrictions of g apply. So we know for g of x, x cannot equal -7. We already know that. So we keep that in our back pocket. We're going to use that later. So even if it doesn't look like that, that's still a domain restriction. Okay, so we know that this fraction bar is divided by, and to divide by a fraction is to multiply by its reciprocal. Let's just do it. X over x minus 6 divided by 8 over x plus 7. That's the same thing as x times x minus 6 times x plus 7 over 8. So this becomes x times x plus 7 over 8 times x minus 6. All right, and now we want to know what our domain. So the domain of this is start at -infinity. All right, and we know that with this function, with the resultant function, that x cannot equal to 6. So we go back, whoops, not equal to 6. So now we have our x minus 7. We have our x, well, x is equal to -7. X is equal to 6. Those can't be there. So we make our whole domain around those two things. So negative infinity to -7 union -7. It's not a 7. -7 to 6 union 6 to infinity. And that will be our domain. The main idea of this problem is knowing that you consider g the domain restrictions of g of x, and then dividing rational functions. Let's continue. Find f. So suppose that the functions f and g are defined as follows. F of g is f of x is 1 over 3x squared plus 5. And g of x is the square root of 2x plus 3. So find f minus g and f times g, and then give their domains. So f minus g, all right, so I guess I'll do it over here. So f minus g of x is equal to 1 over 3x squared plus 5 minus square root of 2x plus 3. That's it. Like, that's f of g. F times g is equal to 1 over 3x squared plus 5 times square root of 2x plus 3, which is just equal to square root of 2x plus 3 over 3x squared plus 5. Easy part. Now, slightly more complex. When we look at the domain of f minus g, the first part is a rational part, which is a fraction. And we see what makes this denominator equal 0. Well, if you look at this, you know that x squared, the lowest it can be is 0. Like x squared cannot go less than 0. So there will never be a case where this is negative. Where this is negative, so that means that this is never 0. So we're cool there. Here we have the square root of 2x minus 3. And that, we know from that 2x plus 3 has to be greater than or equal to 0. All right. So subtract 3 2x has to be greater than or equal to 3 divided by 2. So x has to be greater than or equal to 3/2. That's the only domain restrictions for this that we have. So we know that. So in interval notation, we have -3, not negative. It is negative. -3/2 to infinity. All right, and all that is my answer for the top. For the bottom one, again, the denominator has no restrictions, so we're only restricted by the top, which is the same as the same work as the same work we did there. So our domain, let's see, domain. So our domain is -3/2 to infinity. Same thing. So thankfully, this problem had it where this work applied to both sections or both parts. All right, number 5. Suppose the functions q and r are defined as follows. Q of x is equal to x squared plus 9. R of x is equal to square root of x plus 8. Find the following. Q composed with R of 8 and R composed with Q of 8. So there's a couple different ways that we can do that. We know that if we're composing the functions Q of R of x is Q of R of x. So we can put that, this is Q. So we can put that into that. Or for this instance, we can do, well, let's just do it. So Q of R of 8. Q of R of 8 is equal to, well, R of 8 is equal to square root of 8 plus 8 is equal to square root of 16. Okay, and then we do Q of square root of 16. So we do R of 8, and then we do Q of whatever that is. And that is equal to square root of 16 squared plus 9, which is equal to 16 plus 9, which is equal to 25. So Q of R of 8 is equal to 25. Right, so R of Q of 8 R of Q of 8 is equal to R of Q of 8. Okay, so Q of 8 is equal to 8 squared plus 9, which is equal to 64 plus 9, which is equal to 73. And then we put that into Q. So Q, that's not a Q. So let's do it down here. R of 73 is equal to square root of 73 plus 8, which is square root of 81, which is equal to 9. So R of Q of 8 is equal to 9. I'll try to do a little bit of keeping all that organized. It's kind of messy. So it's kind of like this. There we go. The above the line is one part, and then below the line is the other part. All right, let's go. Let's suppose h of x is equal to 5x plus 3 quantity cubed. Find two functions f and g such that f composed with g of x is equal to h of x. Neither function can be the identity function. There may be more than one correct answer. That is an understatement. There are technically an infinite number of answers here, but we will do the obvious. So we will say that, let's say f of x, g of x. Don't know why this is moving right now. So we're doing g and then f. So we can say g is 5x plus 3. And then we're squaring that. So f of x is x squared. And boom, that's it. Anytime you see a problem like this, most of the time, it's related to composing functions. Most of the time, it's going to be really, really easy. Like, we don't do any tricks with this type of problem because, like I said, there are an infinite number of answers. Okay. So here we go. Number 7. Two functions g and f are defined in the figure below. This is the domain of g. This is the range of g. This is the domain of f. This is the range of f. Find the domain and range of the composition. Write your answers in set notation. Okay. I'll write it over here. So the domain of f of g of x and then the range of f of g of x. All right, so the domain. This is how we would do this. We do g first, like we did in the problems above it. We do g. This is the domain of g. This is the range of g. And the range of g becomes the domain of f. And then the domain, and then the range ends up being the range ends up being the composed range. So the total outputs equal the outputs for the composition function. Let's just see what it looks like. So if I start at 0 in g, I go to 4. There is no 4 in the domain of f. So 0 is not in the domain of this function. 1, let me open up my set braces here. Set braces. We're doing domain first, and then we'll do range. So 1 goes to 3, and then 3 goes to 0. So 1 is in the domain, 3 is in the range. I'm sorry, 0 is in the range. Right, because we went from 1 to 3, and then 3 was in the domain of f to go to 0. So input here, output there. 4 goes to 4. There is no 4, so 4 is not there. 5 goes to 3. Then 3 goes to 0. So 5 is in the domain. 0 is in the range again. We already have that. Okay. 1, 5. 7 goes to 5. 5 goes to 0. So 7 is in the domain. We already have 0, so we leave that there. 8 goes to 7. 7 goes to 0. So 8 is in the domain. Come on. And 0 is the only thing in the range. And that is the domain and range of composition of functions. It has to be in the, for it to be the domain in the composition, for it to be in the domain of the composition, it has to have an input to output, and the output has to be in the domain of f. If it's not in the domain of f, then it is not in the domain of the, if the output of g is not in the domain of f, then it is not in the, then the input in g is not in the domain of the function. That sounds super confusing. I hope the example was a little less confusing, but you can ask me about that if you want. Let's keep going. For the real value functions, that means that this is greater than or equal to 0. G of x is equal to square root of quantity 3x plus 9. And h of x is equal to x minus 2. Find the composition G composed with H and specify its domain using interval notation. So G of H of X is equal to G of H of X. I like to write it like this because it lets me know what's happening, which is G of X minus 2, which is square root of 3 times X minus 2 plus 9. Okay, which is square root of 3x minus 6 plus 9, which is square root of 3x plus 3. Okay. If we look at the domains, the domain of g of x would be x has to be greater than or equal to negative 3. Because negative 3 would make this 0, less than that would make it negative. Okay, the domain of this one, 3x plus 3, has to be greater than or equal to 0. Subtract 3. 3x is greater than or equal to negative 3. Divide by 3. That means x is greater than or equal to negative 1. All right, so for this one, it's x is greater than or equal to negative 3. For this one, it's x is greater than or equal to negative 1. So this domain is more restrictive than that one. So that becomes our domain. So in interval notation, we say negative 1 to infinity. I hope that was helpful. This domain is stricter, is less restrictive than this domain, so this becomes the domain. Let's continue. Suppose the value R of D dollars in euros is given by the function R of D is equal to 9/10 of D. The cost P of N in dollars to purchase and ship N purses is given by P of N is equal to 99N plus 23. Write a formula for the cost Q of N in euros to purchase and ship N purses. It is not necessary to simplify. Okay, thank you. So the top function is dollars in euros. So in P of N is in dollars. So this is dollars to ship. We want to know how many euros. So we're going to put this in to that. Okay, this is dollars to euros. Euros is the output. This dollars is the output. Dollars is the input here. So this is kind of a real world composition. So Q of N is equal to, we're putting P into R. So R P of D. All right, so we're doing R of 99N plus 23, which is 9 over 10. 99N plus 23. That's it. They said don't simplify, and we're not. That's it. Okay, number 10. We're getting close. 1-to-1. 1-to-1, yes. 1-to-1 means that it passes the horizontal line test. Every input only has one, or every output has one input. Okay. Well, if you take this one, this does colors. This does not pass the horizontal line test. So it is not 1-to-1. So this output, any output below negative 1, so negative 2, there are two inputs that give us negative 2. There are two x's that give us negative 2. And the same for everything else down there. So no. 1-to-1 cubic function? Yes. Whoa. 1-to-1 does not pass the horizontal line test. So no. 1-to-1 does pass the horizontal line test, so yes. This is a tricky one, but yes, this is 1-to-1 because at 1 is the definition of the function. So this gets infinitely close, but it never touches this point. So there it is going to pass a horizontal line test all the time. Okay, so let's continue. 13. Two functions defined as follows. The function g is defined as the set of the points -2, 8, 3, -4, 5, -2, and 8, 5. H of x is defined as 3x plus 10. So the first problem, g inverse of 8. So in other words, what is the g inverse of 8? That is -2. Okay, so in other words, if I take the inverse of this function and I put in -8, if the inverse of the function means the inputs and outputs switch. So in other words, this becomes the input, which means that becomes the output. Okay. H inverse of H. H inverse of X. We actually have to calculate that. All right. So H of X is equal to 3x plus 10. First step, Y is equal to 3x plus 10. Do that substitution. Second step, switch X and Y. 3y plus 10. Third step, solve for x. So we're going to subtract 10 from both sides. X minus 10 is equal to 3y. Divide by 3. And y is then equal to x minus 10 over 3. And there are a few different ways that you can write it, but we're just going to leave it like that. X minus 10 over 3. All right. Okay. H inverse of H of -3. Okay, so in other words, if we do H of -3, and the property tells us that inverses can't undo each other, but let's just do it just to be sure. So H of -3 is equal to 3 times -3 plus 10, which is equal to -9 plus 10, which is equal to 1. Right? H inverse of 1. And we have H in, oh, I'm sorry. Last step. H inverse of X is equal to X minus 10 over 3. That's what you're supposed to do, that last step. It's trivial, but go ahead and do that. H inverse of 1, that is equal to 1 minus 10 over 3, which is -9 over 3, which is -3. So you get what you started out with. Sorry about that. Brothers never start texting until I get on the phone. All right. Scientists have found a relationship between the temperature and the height above the distant planet's surface, T of H, given below. Oh, sorry. Scientists have found the relationship between the temperature and the height above a distant planet's surface. T of H, given below, is the temperature in Celsius at a height of h kilometers above the planet's surface. The relationship is as follows. T of H is equal to 30.5 minus 2.5 H. Complete the following statements. Let T inverse be the inverse of function T. Take X to be the output of the function T. Which function best describes T inverse of X? So if T of H is the temperature at height H, then the inverse would be the height H, where the temperature is X. So T of H is the temperature at the height. The inverse would be the height at the given temperature. Okay, that would be the first one. Thought I turned that off. There we go. All right. T inverse of x. Okay, so T inverse of x. That means just calculate the inverse. So that means that we'll take this one. So x is equal to 30.5 minus 2.5 h. So we switch it. H is equal to 30.5 minus 2.5x. And then we solve for h. H minus 30.5 is equal to negative 2.5x. We divide by negative 2.5. I know I skipped a step. I didn't show that I subtracted 34.5 from both sides. Minus negative 2.5. All right, they cancel each other out, and I am left with those cancel. And I'm left with x being equal to negative. Oh, well, I solved for x, but it ends up being T inverse. So T inverse of x becomes negative h minus 30.5 over 2.5. That should be, I thought so. X is the variable. This ends up, this negative, let's make this look like a negative. The whole function is negative. I normally don't like to write these negatives out here like that, out in front like that. But since we can emphasize it, we'll do that. X is negative that. So I'll just move the negative. The negative never goes in the denominator. It either goes in the numerator or out in front. I normally don't do out in front because it's easy to mess up, but it's okay this time. And then T inverse of negative 15. We're going to go ahead and put that in the calculator. And we get 15 minus 30.5 and divided by 2.5. And I get equals negative 6.2. Oh, positive 6.2. I forgot the negative. Don't forget the negative. All right, number 13. Last one. Consider the function f of x is equal to square root of x minus 4 plus 2 for the domain from 4 to infinity, which that is the domain of that. Find the inverse of f and then state the domain. Okay. So f of x is equal to square root of x minus 4 plus 2. Y is equal to square root of x minus 4 plus 2. X is equal to square root of y minus 4 plus 2. Subtract 2. X minus 2 is equal to square root of y minus 4. Square both sides. So x minus 2 squared is equal to y minus 4 plus 4 plus 4. And x minus 2 squared plus 4 is equal to y. So that means that f negative 1 of x is equal to x minus 2 squared plus 4. That is our inverse. Okay. Now, tricky part. Domain. If I put in 0, let's do it like this. F of 0 is equal to, I can't be 0. The lowest f I can have is 4. 4 is the minimum value of my domain of my original function. And f of 4 is equal to 2. So that yields the point 4, 2 as a minimum value. All right, so f inverse of 2 is equal to 4. It'll be the point 2, 4. This is my minimum value. So although this function here actually technically does not have a minimum value, the inverse of this function, because it's the inverse of this function, it does have a minimum value. So my interval becomes from 2 to infinity. So this function, this inverse has a function because the inverse is related to the original function. It's like a reflection. If you really want to see it, you could, well, I'll just tell you, this function is, the parent function looks like this, right? Changing colors, the transformation tells us that we've shifted it right 4 and up 2. So right 4 up 2. So that would make it look like this. Okay, this is rough sketch. The inverse of a function is reflected across the line y is equal to x. So that would be like, that means that the inverse function for the square root function, the square function looks like a square root. So that would be moving it right 2 up 4. So it would look like that. Not drawn to scale 100%, of course, but it's a reflection across this line y is equal to x. Because of that, the inverse function, even though it looks like this, it doesn't complete, it only behaves like this on the inverse, on the output of this function, the original function. Okay. All right. I've gone on enough. If you have questions about this, please feel free to ask.